Hello, everyone. Welcome back to today's lecture number 11. We're going to talk about the third application of our voting game models. The third applications consists of using the inverse voting game to discover hidden peer influence networks inside a school data about substance uses. Before talking about the data set, we have already covered the two first numerical applications of our game. So we have covered the application of the network propagation using the example of the geopolitical data. And secondly, we also covered the data classification aspects using the second application of the KNN missing data imputation in the previous lecture. And now our focus will be using the inverse voting game model to accomplish the network discovery aspect of our model. In the sense that we are going to observe the choices of individuals inside the network, and we're going to use the model to discover the hidden network structure of these individuals. So let's talk about the data set. This is coming from a public available data set of 129 secondary school students based in Glasgow of Scotland. Originally, there were 160 students, but due to some missing data, we only have 129 of them being fully available. They are tracked for several years, and we got their level of consumptions of three different substances, and based on how frequent or how heavy are they on using them. Also, very interestingly, we provide the friendship network of these students. To the right-hand side, we see the research questions will be the following. Can the inverse voting game model recover the latent peer influence network that explains observed substance consumptions without ever being told who their friends are? If the answer is yes, and if the recovery network using our algorithm is close to the given friendship network, it tells us that the peer influence on those substance use is largely affected by those friendship ties. We got different raw data, and we conducted some pre-processing of the data. For example, let's talk about the encoding, because our network and our data are using different levels. It's not originally binary. So one choices we have done is to transform them into a cumulative binary representation. So for example, one feature will be connected to a substance about a level. So the feature returns 1 if the consumption is above certain level in that period. We got the left-hand side as a example. Different features correspond to cannabis consumptions, encode at least some frequency use of those substances, which means once we did this transformation, we'll get more features than the original features in the data set. So now let's talk about the running of the model. We don't get one single configuration, but we test seven different distinct configurations of the constraint set. Each constraint set we write CFG is the configuration. Each of them encodes a different assumptions about who can influence whom. Let me go through each columns. So configuration 1 is completely free, so there are no extra constraints. This is the most permissive setup. For the configuration 2, there is one more constraint. It's called fixed degree, FD for fixed degree constraint, meaning that each student's number of attractive neighbors is fixed to match their observed friendship degree. So a kind of extra constraint on how many friends each individual have based on how it was. We can see how much does it recover the original data set. Configuration 3 is the most restrictive, one of the most restrictives. So attractive neighbors are forced to exactly match the friendship network. So really matched to how the data provided. And of course, as a consequence of that, the degree is fixed. Let's look at configuration 4. Configuration 4 until 7 use what we call the BNN. It's bounded attractive neighbors, meaning that attractive links are constrained to be a subset of the friendship network, not an exact match. So let's say individual I has the friends J1, J2, and J3 in the given network, in the given data. We will fit to our network um, in our data that J1, J2, J3, J4 are their potential friends. So individual I cannot have friends other than those candidates. This is the constraint that we enforce in this case. So this is more restrictive than, of course, free choice, but less restrictive than the fixed choice. So at the right-hand side, the fit columns shows the number of individual feature pair where the recovered network correctly rationalize the observed consumptions. So the maximum time um, a match can happen is 129, the number of individuals, times 27, so the number of features, which is about 3,500. So notice immediately that the configuration 1, the free model, achieved the highest fit at 3,227. And compared to the configuration number 3, forced to match friendship, it makes the fit be worse than before. So what does it mean? The key finding from the configuration 1 of the inverse voting game achieving a higher fit, only a 6.7% discrepancy from the observed friendship network, or in other words, it's almost 93% of correct predictiveness. This recovered attractive network is only this 6.7% away from the observed friendship network, even though the model was never given any friendship data. It discovered a network close to the friendship purely from the configuration histories. And what about configuration 3? If you look at here, when we force the model to use the observed friendship network as its attractive links, the fit dropped from 3,200 something to 2,300 something. This is a lot lower than the configuration 1. This tells us something important, that the observed friendship is not the right influence network for substance use. Actually, the real influence structure related to friendship is not identical to it. There is a latent component behind this. So the interpretation we can see at the right-hand side that the true influence structure is related but not identical to the friendship network. So the peer influence on substance consumptions has this latent component that the friendship data alone does not capture it. However, the inverse voting gain model recovers the network within 7% without observing it. How does it compare to the existing literature? So we got a reference point to the hand side from the work of Chuya et al. 2023, who analyzed the same Glasgow dataset using an influential imitator approach. So their model assumed a fixed influence hierarchy. More popular the student leads, then the other follows them. This is a one-directional and a hierarchical view of the peer influence. And compared to this paper about the inverse voting game, our approach makes none of these assumptions. There is no hierarchy between students. Attractive and repulsive links are both possible, and the network itself is the output of the model, not an input. And most importantly, both attraction and repulsive are considered as informative parts of the model. Some students differentiate themselves from the peers rather than imitating them. This bidirectional influence is structurally invisible in the propagation models that only allows the positive imitative social content and social interaction. So in summary, we applied the inverse voting game to 129 students, and we changed the features to be binary using the procedure we talked about to make it 27 binary features. We tested seven different network constraint configurations, encoding different levels of constraints. So different levels of prior beliefs about the influence structure. The fully free model achieved the highest fit and spontaneously recovered a network only 6.7% not fit away from the observed friendship network. So this was done without using friendship data. The data was not known to the model before. And forcing the model to use the friendship network actually reduced the fit, confirming that latent influence differs from the observed ties. So in the next lecture, we're going to talk about the numerical result, the overall numerical result, and put a conclusion to this work. Thank you very much for watching and see you guys in the next lecture. Bye bye.